In this lecture, we're going to meet extreme stars, white dwarfs and neutron stars, the leftover remnant cores of low-mass and high-mass stars. The lecture today is motivated by trying to answer the question of what happens to the massive compact stellar cores that are left over at the end of a star's life. The quick answer is that gravity wins, and the core will continue to collapse until one of two things happens. Either a new pressure law will come into play that will be sufficiently strong to be able to halt the further gravitational collapse, and the core will settle into a new hydrostatic equilibrium. Or no pressure law can come into play, and the collapse will continue until the object reaches zero radius and infinite density and becomes a black hole. We're not going to talk about black holes in this lecture, but we are going to talk about the other case of a new pressure law coming into play which can halt the collapse of gravity. To understand what these new pressure laws are, we have to take a close look at what happens to gases at high densities. At very high densities, gas particles are not as free to move around as they would be in a low-density gas like the air in the room. And as a consequence, at high densities, we begin to see the ideal gas law beginning to break down. At low density, if we took a super microscope and looked at the atoms and molecules in the air, we would see them relatively free. There's a lot of space between individual atoms and molecules, and they move around with a certain speed. The mean kinetic energy of a gas like this, as we've already seen, is a measurement of the internal energy, and we equate that with the temperature of the gas. A high temperature gas has a high internal kinetic energy, and a low temperature gas has a low internal kinetic energy. The ideal gas law tells us that the pressure of such a gas is equal to the number density of particles, for example, the number of atoms or molecules per cubic centimeter, multiplied by a physical constant called the Boltzmann constant, and the temperature. We're going to ignore the Boltzmann constant. Pressure is the product of the density and the temperature. If we increase the temperature, we increase the mean kinetic energy of the gas, the pressure rises. Similarly, if we increase the pressure at a constant temperature, we have more particles, each of which has the same mean kinetic energy given by the temperature, and the pressure will also begin to rise. But when the density gets high enough, and this is now a simple classical picture of the problem, the atoms and molecules all start becoming close together. Another way of looking at it is that the mean distance between the particles making up the gas becomes small compared to the sizes of the particles. Of course, particles really aren't hard BBs, and so to really describe a gas at very high densities, we have to talk about the mean distance between particles being comparable to the quantum mechanical size of the gas. And so this description of a gas at extremely high densities is tightly wound up with the quantum nature of matter. We're not going to go into that in this lecture because quantum mechanics is somewhat beyond the scope of this course. But you can get a basic idea of what happens at high densities with this simple, what we call classic kinetic picture. The atoms and molecules are now so close together that even though they may be at relatively high temperature, their interactions are pretty much dominated by the fact that they can't move around very freely. There are not many quantum states that they can get into. All the low energy states are occupied, and only the high energy states remain. As a consequence, the energy of the gas, the internal energy of this high-density gas, can be quite large even though the individual particle motions might be quite small. And something quite remarkable happens. The pressure now only becomes dependent upon the density of the gas, not the temperature. In this case, I've drawn a simple degenerate gas in which the pressure is proportional to the density to the 5/3 power. If this were a very high energy degenerate gas where the particles were moving, having to obey Einstein's relativity, that would be pressure proportional to density to the 4/3 power. The bottom line is this. At sufficiently high density, we say that the gas becomes degenerate. In this case, in a degenerate gas, the pressure becomes independent of the temperature, and we have an interesting state of matter. The degenerate gas will strongly resist further compression independent of how hot it is. If the gas gets very hot or the gas gets very cold, the pressure really doesn't change. And so the pressure only depends upon how tightly packed the matter is, not how hot it is. This new state of matter, this degenerate gas, has a very interesting property. It allows very cold objects to be in hydrostatic equilibrium. We no longer need high temperature to have high pressure. All you have to have is high density. And so at extremely high densities of compression, the equation of state, the rules that govern the interplay between pressure, density, and temperature, change from an ideal gas law to a degenerate gas law. Why is this important to us? Well, let's look at extreme states of compression that we see in remnant stellar cores. White dwarfs are the collapsed cores that are left behind by stars which have an initial mass that is less than about 8 times the mass of the Sun. This would be the mass the star would have when it's residing on the main sequence. These objects are held up against gravity by degenerate electron pressure. In this case, it is the gas of electrons that makes up the body of the white dwarf that becomes degenerate. The pressure no longer becomes dependent upon temperature, and the degenerate pressure can rise to the point that it can match the inward crush of gravity and reestablish hydrostatic equilibrium, although it is now hydrostatic equilibrium with a degenerate electron gas, not an ideal gas. What type of white dwarf do you get? If the initial mass is less than about 4 solar masses, you get a carbon-oxygen white dwarf. If the initial mass is between about 4 and 8 times the mass of the Sun, you get an oxygen-neon-magnesium white dwarf. The properties of these stars is that the mass is less than about 1.44 solar masses. You can have very small masses, but you can't have a mass above 1.4 m-Sun. The radii are all roughly the radius of the Earth, about 1/100th of the radius of the Sun. The radius actually does depend a bit on the mass, in the sense that lower mass white dwarfs will have a larger radius than higher mass white dwarfs. The higher the mass, the smaller the radius, because you need to compress a bit more in order for the degenerate electron pressure to be able to offset the gravitational force trying to crush the object in. The density of a white dwarf ranges from about 100,000 to 1,000,000 grams per cubic centimeter, and because we're packing about 1 solar mass into the volume of the Earth, the escape speed from the surface of these objects can be quite large, anywhere from 1/100th to 3/100ths of the speed of light. White dwarfs are very, very extreme objects. They're also very hot. Remember that they reside in the lower left-hand corner of the Hertzsprung-Russell diagram, in the region of low luminosity but very high temperatures, tens of thousands of degrees. But here's the important point. White dwarfs do not have a source of energy. They only shine by residual heat. They do not have nuclear fusion, and they do not contract under gravity because they are in a state of hydrostatic equilibrium in which gravity is balanced by electron degeneracy pressure. The heat, as it radiates into space, is slowly lost, and so these objects will slowly fade out and cool off. Here's a photograph showing a white dwarf star. The big bright star in the middle is Sirius, the dog star, the brightest star in the nighttime sky. Sirius A is a roughly 2 solar mass main sequence A-type star with a surface temperature of about 10,000 degrees Kelvin. This is what we see with the eye, but with the Hubble Space Telescope, or any good telescope on the ground, it was found that Sirius A has a companion, Sirius B. When the masses of Sirius B was measured, it was surprisingly found to be almost 1 solar mass. A more accurate measurement is it's 98% the mass of the Sun, and yet it's tiny and faint and very, very hot. Sirius B is a carbon-oxygen white dwarf with a mass of about 0.9 times the mass of the Sun. As I mentioned before, white dwarfs have no source of internal energy and therefore shine away only by radiating what leftover internal heat they had from their formation. There's no fusion source available in the degenerate gas, nor are they gravitationally contracting because they're in hydrostatic equilibrium. As a consequence, white dwarfs will cool off and slowly fade away. They have an enormous amount of internal energy and often a lot of what we call heat capacity, and therefore this cool-off takes a very long time. The final state of a white dwarf is to become something fortunately referred to as a black dwarf. This is an old, cold white dwarf that is cooled down to the point that it is the same temperature as background space, about 3 degrees Kelvin, 3 degrees above absolute zero. The thing is, it takes a very, very long time for all of the internal heat to leak out of a white dwarf. So long that for a typical white dwarf, it will take something like 10 to the 15 years. 10 to the 15 is 1,000 trillion years in order to cool off to a temperature of about 5 degrees Kelvin. The universe is only 13.8 billion years old. So this means that black dwarfs, totally cooled off, completely cold white dwarfs, are still only notional. The universe is actually not old enough for black dwarfs to have existed yet. The very first stars to have formed in the universe probably formed when the universe was just a little under 1 billion years old, we think. As a consequence, the oldest white dwarfs are only around 12 or 13 billion years old. As a consequence, they are still hot. They're still glowing away, and they're a long, long ways from ever becoming a black dwarf. The name black dwarf is somewhat unfortunate because black dwarf sounds awfully close to black hole. Don't confuse the two. A black dwarf is a notional object which is a super cold, old, ancient white dwarf, whereas a black hole, as we're going to see in the following lecture, is a very different beast entirely. The maximum mass that a white dwarf can have is called the Chandrasekhar mass, named in honor of the 20th century physicist Subrahmanyan Chandrasekhar, who discovered early in the 20th century that an electron-degenerate gas can't work indefinitely to hold up itself against gravity. That in fact there is a maximum mass, which he computed to be 1.44 times the mass of the Sun. White dwarfs are supported against gravity by electron degeneracy pressure. If the mass exceeds 1.44 times the mass of the Sun, electron degeneracy pressure will fail. It won't be enough to be able to hold off gravity, and the white dwarf will begin to collapse. So far as we know, there is nothing we think that can halt that collapse, at least not without something else coming into play to change the rules of the game. There are two questions that one arises about the Chandrasekhar limit. One of these is, how could you make a white dwarf heavier than the Chandrasekhar mass? What could you do to a white dwarf to add mass to it to make it heavier than its Chandrasekhar mass? And the second question is, what would happen if you did that? If a white dwarf's mass exceeds 1.4 m Sun, it turns out it doesn't actually collapse into a black hole. It actually explodes, and it explodes as a type 1a supernova. When electron degeneracy fails, the white dwarf begins to collapse. When the white dwarf collapse begins, however, instead of collapsing completely in upon itself, before it can do that, it ignites carbon and oxygen fusion at extremely high density inside of itself as a runaway thermonuclear explosion. This fuses explosively all the way up to iron and nickel. This is very different than the kind of nuclear fusion ignition that we've seen before. Normally, when nuclear fusion is ignited deep inside the core of a star, the nuclear fusion is stable. It's held together by a hydrostatic thermostat. The reason for that hydrostatic thermostat is surrounding the core is all of the envelope of the star, if you will, tamping down the nuclear fusion. But when nuclear fusion, in this case carbon-oxygen fusion, ignites at very high density inside of a white dwarf, there is no envelope to tamp it in. And furthermore, this ignition occurs in a degenerate gas. When fusion occurs in a degenerate gas, the temperature begins to increase, but that temperature increase does not lead to an increase in pressure. There's no hydrostatic thermostat in play, and so the star continues to collapse while the temperature keeps growing and growing and growing. The only thing the energy being generated by fusion can do is heat the surrounding material. That heating of the surrounding material causes fusion to run faster, which produces more heat, which causes fusion to run faster, and you end up with a thermonuclear runaway. This thermonuclear runaway completely destroys the star as a type 1a supernova. A type 1a supernova explosion are the brightest supernovae of all. They produce no remnant. They completely disrupt the white dwarf and leave behind nothing except the byproducts of nuclear fusion, primarily iron and nickel. Type 1a supernovae, as we're going to learn later, are extremely important for making most of the iron that we see around us in the universe. This picture over here on the right is a Type 1a supernova that occurred in a distant galaxy named NGC 4666 that occurred in 2014. Its name is Assassin 14LP. I bring this one up because this was discovered with a pair of telescopes that were built by The Ohio State University to find such supernovae in distant galaxies. Here is this Type 1a supernova going off just off-center from this distant spiral galaxy. Type 1a supernovae can be distinguished from core collapse supernovae of massive stars by their pattern of brightness when they explode and by the spectrum that they produce when they explode. A rapidly expanding hydrogen gas cloud, as you would see in an exploding massive star, will contain lots of lines of hydrogen. A Type 1a supernova, a thermonuclear runaway explosion of a carbon-oxygen white dwarf core, is not going to have any hydrogen lines. And so that gives us a way of distinguishing a Type 1a supernova from a Type 2 supernova, as we call them, a supernova from a massive star core collapse. Type 1a supernovae have been seen in our galaxy. Indeed, Tycho's 1572 Nova Stella in the constellation of Cassiopeia was one such Type 1a supernova. On the left shows the Nova Stella from Tycho's book of the year 1577, showing the position of this very, very bright star that suddenly appeared in the sky and then faded out over the course of a month or so. We can't see a remnant there today, but if we point an X-ray telescope at that direction, we can see the expanding explosion cloud shown over here on the right. This is the extremely hot gas and iron-rich debris that is coming off of this completely disrupted white dwarf star. Similarly, Kepler's supernova of the year 1604 that was seen in the constellation of Ophiuchus was also a supernova of Type 1a, an exploding white dwarf. Here's a classical-looking sketch of the constellation of Ophiuchus, the snake bearer, and down here near the heel of Ophiuchus is Kepler's nova. Looking at a composite of visible, infrared, and X-ray light, we once again see this very characteristic appearance of a Type 1a supernova remnant. This is the complete disruption of a white dwarf, and what we see is a more or less spherical debris cloud of mostly iron-rich debris and extremely hot X-ray emitting gas expanding away from the site of the explosion. There's no remnant left behind. The white dwarf has been completely disrupted and has gone away. That's what happens if you tip a white dwarf above the Chandrasekhar mass. But how do you actually do that trick? How do you actually make a white dwarf's mass exceed the Chandrasekhar mass? There are two possible ways that astronomers have determined are plausible ways to make a white dwarf become over the Chandrasekhar mass. You can't make them that way. The mass of a white dwarf is pretty well limited by the properties of the core inside stars, and there's no way that we've yet found to make a white dwarf core actually explode inside of a normal star. So you have to take the white dwarf after it becomes a white dwarf and add mass to it. One of the ways that you can add mass to it is to have accretion in a binary star system. In this case, the white dwarf is one member of a binary star system in which the white dwarf gets matter from its unevolved donor star. So we might imagine, for example, a binary star system which had a high mass star, an intermediate mass star, and a low mass star. Remember that intermediate mass stars evolve faster than low mass stars, so the intermediate mass star is old enough to have evolved through all the red giant phases, blown off its envelope, and now leave behind a white dwarf. The envelope blow-off, as you may recall from previous lectures, is very slow and gentle. It takes a few 100,000 years. As a consequence, the binary star system is not disrupted because the mass of the white dwarf is still present. If the white dwarf and its somewhat lower mass companion are able to get close enough that the gravity of the white dwarf can begin to bleed off some matter from the star, it can slowly but surely accrete that matter. It falls into a disk and slowly dribbles onto the white dwarf. If the white dwarf started out at about 1 times the mass of the Sun, and we wait long enough, enough gas can be drawn off of the donor companion to slowly raise the mass of the white dwarf above 1.44 solar masses, and when the mass just tips over the Chandrasekhar mass, boom. Turns out the binary accretion, however, to be able to be the channel for creating one of these type 1a supernovae, is a rather difficult channel to work. Because while you have to grow the mass on the white dwarf to get it above 1.44 solar masses, if you put the matter on too fast, the matter will heat up so much as it's compressed down onto the surface of the white dwarf that it will actually undergo a runaway hydrogen fusion reaction on the surface. This runaway hydrogen fusion reaction will blow off the material that had just been put onto the surface of the white dwarf and even take a little bit of the mass of the white dwarf away with it, producing a very bright thermonuclear flash. These bright thermonuclear flashes are seen. They're called classical novae. They're not as luminous as a supernova, but we see a lot of classical novae in our galaxy and in nearby galaxies. So the binary accretion model, while it can work, has certain limitations. Another way that we've determined is possible to make a white dwarf get above the Chandrasekhar mass is to start out with a binary system containing two white dwarf stars. The original two stars of the binary system have both evolved to the white dwarf phase, and the white dwarfs now begin to orbit around each other, slowly losing energy, in this case, to gravitational radiation, the wiggling of space and time predicted by Einstein's theory of general relativity. As the orbit begins to decay, the two white dwarfs begin to spiral closer and closer and orbit faster and faster. Eventually, the two stars will coalesce, but their combined mass, if it's greater than 1.44 solar masses, will cause the new, larger remnant to explode as a type 1a supernova. This is the double white dwarf merger, or sometimes called the double degenerate model for the production of a type 1a supernova. The problem with the double degenerate model is that such white dwarf mergers are likely to be very rare because the two white dwarfs have to start out very, very close to each other in order to begin the in-spiral. And the gravitational in-spiral takes a very long time. And so we shouldn't see as many type 1a supernovae if the double degenerate solution is correct. An interesting way around it, a way that's been investigated, for example, by astronomers here at The Ohio State University, is that this binary merger may be assisted by the gravity of a third star, because we see that quite a number of stars in the sky are not just doubles, but actually triples, in which the third star is far away. And there are long-range gravitational interactions, sometimes called the Kozai leadoff mechanism, that could actually lead to hasten the merger of two white dwarfs. This is still an unanswered question in astrophysics. We see type 1a supernovae. We have a reasonably good model for describing the explosion we see as a disrupted carbon-oxygen white dwarf. But what we don't have is a good definitive model for how these white dwarfs actually get together, grow mass above 1.4 solar masses, and explode. This remains still fully unsolved problem of modern astrophysics.